All right, so as the second part for this experimental methodology section, we're going to talk about ablation studies. So let's say you've finished building your model, you've divided your data into training sets and validation sets to help you tune the parameters, and testing sets to compute various metrics on your data to show how well it performs and predicts whatever you're predicting or label or translate. And you have accuracy and performance measures and precisions. You want to claim that you're doing state-of-the-art performance or unprecedented solutions to something that has never been solved before. Or maybe your algorithm is the first feasible solution for some problem and no one has tried this before. These are all different ways to try to get some research published on an algorithm that has some new results or results that are better than previous results. But even if you have nice plots and statistics claiming these results, there's still some other questions that someone could ask you about your model, such as these questions here. They could ask you, why does it work? Which part of your model is the most important? Where is the computational bottleneck, right? So what's the thing in your algorithm that's costing the most computation time? If it takes a week to train it and you're spending 3 days on one particular part, you're going to say, well, is that part really essential? What's the part of your architecture, of your system, that's actually getting you the results, or is everything important, right? So the methods we've talked about before of dividing your data and even these accuracy and performance metrics won't answer that kind of question for you. If you want to answer that kind of question, you need to dig deeper into your model, and one way to do that that's become popular in the last few years are called ablation studies. So ablation comes from biology or medicine as a method that gets used there, and it's the removal of something from a system, in their case, from a patient or from an animal if you're doing experiments, and trying to figure out what's causing a problem, right? So if it's cancer, you're removing a tumor and seeing if that kind of helps remove something. But there's various diseases where they actually take portions of a brain out to try to actually change something or remove an organ because it's causing problems in the body. So that's the idea. And in the last kind of 5-10 years, it started becoming more common in machine learning to say, well, we're going to have an ablation study on our algorithm or on our architecture. So once you have a model that's built of a number of different components, each of them is doing a different part of the job of turning your data into a pattern, into an answer that you want. One way to answer some of these questions that we talked about here is to remove certain parts of your algorithm, run it on the data in a fair and unbiased way, and figure out how much impact you get for each one. So other motivations, there's some this thread here on Twitter, a good discussion from a bunch of people when they talked about it a few years ago, and it caused some waves, and then people in those conferences started using it a lot. That's why it is quite recent. And their idea is talking about that kind of gives you this causality of like which part of your model is actually leading to your performance. I'm not sure that's the best way to kind of describe it, but it's another way to think about it. So if you have some model and you have your image processing module here, and you have some neural networks here, and then you have an SVM over here, some other algorithms, which part of the tree that gets you from your inputs to your outputs is the one that is actually giving you the most impact, right? And it's something you have to analyze separately. So in their analysis, and a lot of people, is that you should spend a fair amount of your time when you're experimenting, like we've talked about, dividing up your data and trying to do this validation to fit the parameters of your algorithms. But another kind of parameter is which algorithms to put together, which architecture to use, and spending about 10% of all your experimental time on doing that, determining that answer is reasonable. There's another area where they do automated parameter tuning. So some of the algorithms we'll talk about in the course, you can give them into another system and use optimization. If you take the courses on optimization, those kind of try to seek a really optimal or at least locally maximal answer to some kind of mathematical problem. You can cast the problem of designing your machine learning algorithm, your data processing platform, into that and optimize the parameters that you use, right? And for the people who make these kind of tools, that is Holger Huss and the people who have talked about ablations here, they make these kind of meta algorithms through parameter tuning. They also do ablation studies because you're trying to figure out which part of your algorithm is the most important. So what it is and isn't. Ablation studies is a good way to figure out what parts of your model are useful, and which ones are necessary, and which ones might be unnecessary. Right? You can get rid of some of them. It could help you understand and explain the model you have to others. So if you want to be able to show that this part's important for this aspect, and this other part's important for a different aspect, you'll know that because when you took it out, you'll see that the accuracy of object detection in the image went down, but maybe the recognition of colors or patterns in it was still high. So you'll know which part of your model contributes to the performance. And if you're using it to actually still design your algorithm, it can help you produce this, and essentially it's a type of model or design process that you can do ablation studies before you're done, right? So given that, if you're trying to use it for this designing, think of this as a question. What type of data set should you do your testing on if you're going to be using it to actually help you design your algorithm to work best? This relates to the previous module on dividing up your data properly. Should you do your ablation tests on the test data set, on the training data set, or on a validation training data set? I'll let you think about it for a moment. You can pause the video and think about it. 3, 2, 1. That's just my countdown. So I would say the answer is 3, that you want to definitely do this on a validation data set, because the goal, right, remember we have our entire data set N, and we've been saying, you use a lot on training and some part on validation, and then the rest on test. Maybe you're going to increase the size of your validation data set now if you're going to do an ablation, right, and edge it more over here. Because what you'd really want to do is say, well, let's try a bunch of different architectures, plug in one algorithm, plug in a different algorithm, and see how much they work, or try getting rid of one of them, and do all of those on validation data sets that you're not going to really use for your final test if you're using it to design. And once you've come up with the architecture you like, you have to fix that, and then the final test data set that you've held out, that's the one you publish your real accuracy numbers on. Because if you use the validation sets that you use to make this decision about the architecture, you'll run into the same problem we talked about before with bias about just your accuracy results, because you're essentially reporting results on data that you used to train the model, and choosing which architecture to use is still part of your training process, even though it's you as the human making the decisions, not the algorithm. Other things you can't use ablation for is for regularization, right? So if we've talked about that, or you've seen those videos already, remember what ablation does. What a regularization method is for. Right, it's for avoiding overfitting, right? So you have a model that is very good at getting the right answer for some data, for predicting what's going to happen, or gives the right classifications, but is only good on the training data you gave it, right? So ablation doesn't help you avoid that, because you have to use a different set of data to fix it anyways, and you still want to hold out your test data to be completely separate from your decisions about which modules to include. It also shouldn't be used to help you improve performance unless you're really using it to completely redesign your system. So you really want to report the ablation studies and just show all the results and then say, well, this is kind of interesting. It seems like this part of the network isn't that useful. And then you can propose an improved method, but you'd need more data to test it. And you shouldn't also use it just as a way to fill up space, to make your paper longer, because it does take up extra time. Like, it's essentially an additional type of an experiment you would do, and it's kind of tempting for people if they have you don't have enough work, you don't think you can fill the space. You do these kind of experiments, but the experiments are useful on their own, and the advice I always give on that is if you can't fill the 8 or 9 pages that they want for these conferences anyways, and you're proposing an experiment just to fill more space, then maybe you don't have enough for a paper yet, because you should be able to explain more about your theory or your background or your experiments to fill that. Usually the problem is you have to do an ablation study because it'll really make a stronger argument while every component of your model is needed, and your paper is already full in terms of filling all these pages. So how do you show it and not use up too much more space? So we can talk about different ways to do that, but it's a hard nut to crack. Okay, so let's look at an example of this to make it a bit more concrete. This is a good example explained at the following link here. And the paper that does the ablation study is this Gershik paper, and it's object detection in images. Right. So the task is you're given an image. Here's an image of a field with a fence and a cow in it, and you want the algorithm to detect the cows, all the objects in it, the cow, the tractor, the fence. It's got to detect objects, right? So there's these 2 papers that are doing this. The second one here, Gershik, was using an already complicated algorithm from this paper here in 2012, and they had multiple components of their algorithm, right? So they used feature extraction using something called SIFT. If you've taken image processing classes, you'll have seen that. They also used then supervised training algorithm, kind of a classic pre-neural network one, which we talk about in this course, called SVM. And then they loop over their labeling of objects and kind of get some confirmation from the labels, and then improve their hypothesis iteratively. Right? So they've got this multiple stage kind of thing here. The images coming in is the inputs, is your X, and in the end, the model, the SVM, will give you the labels saying for every image where the objects are, or what objects are present. All right, so there's this original paper, and there's multiple components in here that need to be trained. So there's a linear kind of separation of the images into kind of areas. It's all about detecting what subsection of the image is useful, and then they come up with examples, and the SVM does its training, and it gets feedback and keeps going. So they had their original paper with its own results, and then this Gershik paper tried to build on top of that. So they had their own algorithm where they take the input image, they run the SS algorithm in this stage, so they get the outputs of these guys' plans, all the boxes that tell you where the objects are, and they input that into another one, a new model with using neural networks called CNNs that we're going to talk about in the course, and stretch and move them around, and they get an output that has a different level of confidence, right? And so when we talk about CNNs and deep networks, there's different types of them. So there's these CNN layers, which are meant for images, and then there's, I guess I would say, fully connected layers, which don't kind of deal with images. They are just kind of standard neural network layers. They have multiple components in their algorithm as well. So they've got all the components of the previous algorithm and this one. And so then their ablation study was basically to turn on and off different parts of both of those models to figure out how they contributed to their overall results. Right, so they have original test sets, and as you can see there, they're using a validation set, which they've kind of held out for this, just for this ablation study, and this is validation 2. They have a validation 1 set, which they use to train the SVM itself, and they add different amounts of data to that in their different ablation kind of buckets. Each one of these columns is like a different experiment, right, that's being done. And then for the CNN, initially they just do training without the neural network part, their new part. And then for these two ablation parts, they add in their own new neural network component. And then they have some regularization methods that they use, and they only test that at the end. And they even have different types of features, so how many layers they're using in the neural network. They tried, like, well, should there be 6 layers of features or 7? And then you can see they used map estimation, like we talked about in the probability statistics review section. And they get a bunch of different results, right? So the ones that have the simplest model from the original paper has the lowest. And as they add more of their components, the performance of their algorithm gets better and better. So this would kind of be the ideal setting where you're showing that every combination of the different things you've proposed are actually necessary because they increase the performance, and when you have them all together, you get the highest performance. This may not always be the case, right? If it turned out that the CNN wasn't useful, then this number could be lower, and you might only need the other part, right? One thing they did find in theirs is that that they found that the original features being used by the first paper with SIFT and NSVM weren't as useful. So they had a training set in here where they don't use that, and they only start with some other data set, and it performed even better. So one of the things they discovered by doing this ablation approach is that a high capacity convolutional neural network is sufficient for this to do better. So they could just skip this feature altogether and go straight to these. But they also did a thing where they pre-trained the CNN on other images that were unrelated. And this was kind of a new discovery, and people kind of use this and find it useful in other places as well. That you can train one model and then use it on another data. But in order to evaluate that, they had to do this ablation approach where they try it with and without those new models.